All right. Don't be nervous. I think most of you did a great job.
Most.
Let's think a little bit now. Where we are is we know how to describe a system, so we know how to model a system in state space. We have three basic properties of the system: stability, controllability, and observability. We know that a system can be controllable but not stable. Because a system being controllable means that it can be put in the controllable canonical form, like this. We didn't say anything about the numerical values of A0, A1, A2. It can totally happen that these numerical values make the transfer function, the poles of the transfer function, to be unstable. So controllable system can be unstable. And then it may be very now immediately relevant to ask the question, if a system is not stable but controllable, how can I make it stable? And what's the degree of freedom I can use to do that job? How freely can I stabilize the system? That's the topic for state feedback control. Let's start with a 3x3 simple case. The system is third order. We have the transfer function. We have the system AB matrices. The state feedback control is saying this. The principal logic is that I have this system matrix, and then I use the state as a feedback to my control signal. So U is negative k plus x, very simple. K is a matrix. If x is dimension n by 1, then k, you need to have n columns to make the dimension match. And then let's do a simple case. U is a single input. So this is 1 by m matrix for k. The state feedback logic is extremely simple but extremely powerful. More specifically, if k is 1 by n, let's say its numerical values are k1, k2, and k3. If you have 3 states, then I have 3 coefficients for the k matrix. So as example, I get k1, k2, k3. You can see the dimensions match. After this multiplication, U must be a scalar. So it's indeed single input. The stability analysis relates to how my system A matrix will look like, right? So if you plug in your control sequence, control input into the state dynamics, you get x dot equal to AX plus BU becomes negative BKX. And then it equals to, as example, if A is 3 by 3, that example over there, the controllable canonical form, we get 0, 1, 0 plus, look what's going to happen here. B is 0, 0, 1, my controllability canonical form. K is K1, K2, K3. So when you do this product, you are going to have is negative of, the first 2 rows are completely 0. The last row is going to be K1, K2, K3. So your controllability canonical form makes the new system dynamics. This is a new system dynamics. This is the equivalent A matrix, A tilde matrix, that can tell us about the stability of the system under your feedback control law. So it equals this thing, X. And look at how simple things are. These two matrices added together is simply K1 minus A0. I'm going to actually use negative A0 in the front. Negative A0 minus K1, negative A1 minus K2. So that's the equivalent A matrix for this so-called closed loop system. After you apply control law, the system becomes in a closed loop. You can write this feedback control as follows. So you have your system realization sigma, and then you have your state coming out of the system dynamics. You multiply it with your controller gain, K, and then if it's negative feedback, you add a negative sign here. You close the loop in this way. For this new system, this is the corresponding A matrix. If the original system is unstable, right? If these parameters makes your denominator of the transfer function to have unstable poles, let's now take a look at what is the pole, what are the poles for the system that has the closed loop. The closed loop system, the denominator will be, if this is the A matrix, then the poles or the transfer function. It's the same logic here. The transfer function corresponding to your A matrix in this form is S3, A2, S2, A1, S, and A0. So the transfer function corresponding to this A matrix will be S to the power of 3 plus the last entry here, negative of the last entry. So it's going to be plus A2 minus K3.
Professor, is the sign you in front of the K a plus or minus?
Let's check. Negative A0 minus K1, negative A0 minus K1, minus K1. Happy? So it's going to be A2 K3, A1 K2, and then A0 K1. That is the numerator of the transfer function. And then if you're just thinking about control stability, you don't have to worry about the numerator. So now you see I can directly change all the coefficients in here. If you want me to change this coefficient, I change K3. If you want me to control this coefficient, I change K2. So the structure of the controllable canonical form makes us to be able to arbitrarily change all the coefficients in the denominator. In other words, we can arbitrarily change stability. Arbitrarily. More specifically, we can arbitrarily change the poles of the system and hence change the stability. That is the power of state feedback control. If we can do this, then we can design the poles to anywhere we want. So that's the conclusion. Very powerful control technology if it is in controllable canonical form. So two questions. First, what if it's not in controllable canonical form?
Get it there.
Exactly. So we just learned earlier, if it's controllable but not in controllable canonical form, we can transform the system to be in this canonical form. Second question is, in reality, how do we do this? This is conceptually very powerful. In reality, how should my design be if I have a system if it's not stable, and I want to make it stable? So in reality, we would go inverse in the direction, right? In reality, we can design the poles. I have some desired poles of the system. I can, once I know the desired poles, I can know the coefficients of these denominator terms. And if I know the coefficients of the denominator terms, A is already given by the original system. So A0, A1, A2. These are known, these are known, these are known. Then we can solve K1, K2, K3. So that's the implementation logic, is the reverse direction of the analysis logic.